Before rubber met asphalt in America's logging empire, there was mud. Endless, boot-sucking, wagon-swallowing mud that turned every timber harvest into a seasonal gamble. Picture 15 tons of Douglas fir, enough wood to frame 20 homes stuck axle-deep in spring thaw, horses collapsing from exhaustion, entire seasons of cutting abandoned until winter froze the forest floor solid. Then came a machine that looked like someone welded a tank to a truck and pointed it at the wilderness. The Linn Tractor. Half wheels, half tracks, all brute force. This wasn't just another logging truck. This was the iron beast that turned impassable forests into year-round profit, that crawled through conditions that killed horses and buried conventional vehicles, that transformed American timber from a winter-only industry into the lumber empire that built a nation. This is the story of mud, metal, and the men who refused to wait for winter. The logs are cut, stacked 20 feet high along forest roads that took months to carve from wilderness, and they're going absolutely nowhere. It's April 1915 in the Pacific Northwest, and every logging operation from Washington to Northern California faces the same maddening reality. Their entire winter's work, millions of board feet worth fortunes in Portland and Seattle, sits uselessly piled while the forest floor transforms into something between soup and quicksand. This is mud season, the logger's curse, when profits literally sink into the earth. Walk these forests in spring and you'll find the graveyard of ambition. Wagon wheels buried to the hub, chains snapped like thread, tree trunks abandoned mid-haul because the horses simply couldn't move another foot. Some operations tried teams of 20 horses to move loads that 10 could handle in winter. The animals would strain, hooves churning the ground into deeper muck, until one would stumble and the whole team would collapse in a tangle of leather and panic. Loggers told stories of horses that had to be shot where they fell, too exhausted or injured to save, swallowed gradually by the mud that defeated them. The economics were brutal and simple. You cut in winter when the frozen ground let you move timber, or you didn't cut at all. Spring, summer, and fall were planning seasons, maintenance seasons, waiting seasons. The great timber stands of the West held enough wealth to build cities, but they were locked behind a calendar that made logging a part-time industry. Mill owners watched their equipment sit idle 8 months a year. Workers migrated to other industries when the mud came, taking their skills with them, returning only when frost promised passage. Some operations tried corduroy roads, logs laid perpendicular to create a temporary surface, but these were consumed by the muck within weeks, requiring constant replacement. Others experimented with early tractors, steam-powered behemoths that promised freedom from horses. These iron dinosaurs promptly sank. Their weight, concentrated on narrow wheels, made them more effective at digging holes than hauling logs. Operators watched thousands of dollars of machinery disappear into the forest floor, proving that simply adding power wasn't enough. You needed to distribute that power, spread that weight, float on top of the mud instead of fighting through it. In the upper Midwest, where Minnesota and Wisconsin timber fed a growing nation's appetite for lumber, the problem was different but equally paralyzing: snow. Deep, heavy snow that buried forest roads under 6-foot drifts. Here, loggers actually prayed for cold because winter meant ice roads, water deliberately poured and frozen into smooth highways that let heavy sledges glide. But these required perfect conditions. Too warm and they melted. Too cold and the ice became brittle and dangerous. The window for efficient hauling was narrow, unpredictable, and utterly controlling. One man watched this seasonal paralysis and saw opportunity where others saw inevitability. Holman Harry Linn wasn't a logger. He was a machinist from upstate New York who'd spent years studying traction, watching how different surfaces distributed weight, observing how military tanks crawled over trenches in European war footage. He understood something fundamental. The problem wasn't power, it was contact. A wheel concentrated force into narrow points, but a track spread 15 tons across square yards of surface area, floating where wheels sank, gripping where rubber slipped. In 1916, Linn started building something that would sound insane on paper, a truck that was half conventional vehicle, half military tank. Front wheels for steering, rear tracks for traction, a hybrid that combined the maneuverability of automotive design with the ground pressure distribution of tracked vehicles. Loggers, of hearing about it, laughed. Engineers called it overcomplicated, but Linn understood what the forests demanded. Not elegance, but effectiveness. Not theory, but results. He was building a machine to break mud season's stranglehold on an entire industry. The first Linn Tractor that rolled into a Washington logging camp in 1917 looked like someone's fever dream of what a truck should be. From the front, it appeared almost normal. A conventional cab, steering wheel, engine compartment, and 2 pneumatic tires that suggested this was just another motorized vehicle trying its luck in the woods. Then you walked around back and reality twisted. Instead of rear wheels, there were steel tracks, each one 3 feet wide and 10 feet long, wrapping around a bogie system that looked stolen from a miniature tank. The operators circled it with the skepticism of men who'd seen promises before. 14 feet long overall, 7 feet wide, standing tall enough that a man could walk upright beneath the rear axle assembly. The tracks themselves were engineering compromises made manifest. Each link was forged steel, 3 inches thick, with grouser bars welded perpendicular to dig into whatever surface lay beneath. These weren't the rubber tracks of later vehicles. This was naked metal designed to bite earth, snow, and ice with the same indiscriminate aggression. Power came from a 4-cylinder gasoline engine mounted up front, initially a 35-horsepower Buddha, though later models would pack up to 60 horses. That doesn't sound like much until you understand the gearing. Linn designed a transmission system that sacrificed speed for torque, offering up to 8 forward gears in some models. Top speed was maybe 15 miles per hour on flat, frozen ground, crawling by automotive standards. But in first gear, with those tracks biting, this thing could pull stumps from frozen ground or drag loads that outweighed 2-to-1 up inclines that would stall conventional trucks. The front wheels served a dual purpose that wasn't immediately obvious. Yes, they steered, conventional tie rod linkage connected to a steering wheel that took genuine muscle to turn, especially under load. But they also carried about 40% of the vehicle's weight in empty, providing crucial weight distribution. This prevented the nose from diving in soft ground and kept the tracks from becoming the sole contact point. It was a balancing act. Too much weight forward and you'd lose track traction. Too much aft and you'd plow face first into obstacles. Starting one required ritual. First, you checked the oil. These engines consumed lubricant like fuel, and running dry meant seized pistons within minutes. Then came the magneto, which needed hand cranking to generate spark. On cold mornings, operators would build fires under the engine block, heating the oil until it flowed, because cold viscosity could prevent the crank from turning at all. Once running, the engine settled into a rhythmic clattering that mixed piston fire with the mechanical symphony of chains, gears, and track rollers, a sound one logger described as like God's own sewing machine if God made clothes from mountains. The track system was mechanically fascinating and brutally simple. Each track ran over 5 bogie wheels, smaller steel wheels that supported the weight and allowed the track to articulate over uneven ground. A drive sprocket at the rear, powered directly from the transmission, engaged teeth in the track links, pulling the whole assembly forward. An idler wheel at the front kept tension consistent. When one track needed more power than the other, say when turning or when one side hit softer ground, a differential in the rear axle allowed independent speed adjustment, letting the vehicle steer by varying track velocity rather than angling wheels. Operating it was nothing like driving a truck. The steering wheel controlled the front wheels, yes, but effective navigation required understanding weight transfer and track bite. To turn sharply, you'd slow the inside track using the differential lock while maintaining or increasing power to the outside track. The vehicle would pivot, the front wheels skittering somewhat uselessly as the rear tracks did the real work of changing direction. Experienced operators learned to drift through turns by deliberately breaking traction on one track, swinging the rear end like a pendulum while the front wheels caught and guided the final heading. The cab was Spartan exposure to the elements. Early models had no roof, just a windscreen that deflected some wind and exactly none of the rain, snow, or flying debris that forests threw at operators. The seat was a steel pan with a thin cushion, mounted directly to the frame so every bump, every track articulation transmitted straight through the driver's spine. Controls clustered within arm's reach. Throttle lever, clutch pedal that required full leg extension to depress, brake lever that actuated blocks against the rear track drums, and a bewildering array of shifters for the multi-speed transmission. Maintenance was expected, frequent, and brutal. Track links wore through at predictable intervals, about every 500 hours of operation, requiring replacement link by link using sledgehammers and drift pins. The track tension needed daily adjustment as the steel stretched under load. Grease zerks dotted every bearing surface, each requiring manual greasing every shift. Operators carried toolkits that weighed 50 pounds because breaking down 10 miles into roadless forest meant fixing it yourself or walking home. These weren't machines you maintained to prevent problems. You maintained them to manage the inevitable failures that came from pushing steel through conditions that would destroy anything less brutally overbuilt. The demonstration happened on ground that had defeated everything else. The logging superintendent walked Holman Linn past the abandoned wagons, past the steam tractor that sat axle-deep like a monument to failed innovation, out to where spring runoff met clay soil and created something with the consistency of wet cement. "Pull a load from here to the landing," he said, pointing to a sorting area a half-mile distant. "Do that and we'll talk contracts." They chained 6 logs to the Linn's rear hitch, roughly 8 tons of Douglas fir, bark still oozing sap, the kind of load that would require 12 horses in good conditions. The tracks settled into the mud with a sound like tearing canvas as the weight distributed across all those square feet of steel. Linn climbed into the cab, worked through the starting ritual, and engaged first gear. The engine note dropped an octave as the clutch grabbed. The tracks began to move. What happened next violated every logger's instinct about how traction worked. The tracks didn't spin uselessly like wheels did in mud. They walked. Each link bit into the muck, found something like purchase in the layer beneath, and pushed backward as the next link came down. The mud squeezed up between the track links, oozed over the top, but the continuous contact meant the machine never broke traction long enough to bog down. It was like watching something swim through earth. The trees started moving, slowly, maybe 1 mile per hour, but consistently, without drama, without the desperate thrashing that characterized horse teams in these conditions. The superintendent jogged alongside, watching the tracks, waiting for the moment when physics would reassert itself and this contraption would sink or stall. That moment never came. The Linn churned forward, the logs scraped dual furrows through the mud behind it, and a half-mile later they arrived at the landing with the operator looking bored and the machine still idling in first gear. Word spread through logging camps like fire through slash. A machine that could haul in mud season. Within months, Linn Manufacturing in upstate New York was backlogged with orders from operations that had watched their profits sit stacked and useless every spring. The early adopters became evangelists, bringing superintendents and owners to watch demonstrations that seemed to defy physics. But mud was only half the equation. In Minnesota's North Woods, where Linn eventually moved his manufacturing operation, snow defined the challenge. Here, conventional trucks were worse than useless. Their wheels cut trenches that trapped them within yards. Even tracked vehicles struggled because deep powder offered nothing to push against. The tracks would spin against snow that compressed and offered no resistance. The Linn solved this through sheer contact area and weight distribution. Those 3-foot-wide tracks spread the vehicle's weight so effectively that it rode on top of snowpack that would swallow a man to his waist. The grouser bars on each track link didn't just grip, they compacted snow beneath them, creating a temporary platform that supported the next link. It was self-building traction, a mobile platform that constructed its own roadbed instant by instant. Winter operations transformed overnight in camps that bought Linn's. Previously, logging in deep snow meant waiting for the freeze to harden drifts into something like a surface, then hoping it stayed cold. With the Linn, you could cut in active snowfall, haul during blizzards that made visibility a guess, work through the shoulder seasons when snow was too fresh or too rotten for other equipment. One operator in Michigan reported hauling through a 30-inch snowfall, the tracks compressing powder into ice as he crawled forward at walking speed, emerging at the mill yard hours later with a load that would have been impossible with any other vehicle. The noise in snow was different than in mud. Mud gave you wet slapping sounds, organic squelching. Snow produced a mechanical crunch, each track link compressing crystals into temporary solidity, a rhythmic percussion that carried through still winter air for miles. Loggers learned to recognize the sound of a Linn working distant slopes, the steady heartbeat of links biting snow, telling them that timber was moving, even when visibility dropped to arm's length. Ice presented different problems that revealed both the machine's capabilities and its terrifying limitations. On frozen lakes used as highways in Minnesota winters, the Linn could maintain speeds impossible for horse sledges, but hitting bare ice on a slope became a lesson in momentum management. The tracks had no problem moving forward. Stopping was where physics turned hostile. Brakes on the track drums could slow the tracks themselves, but if the tracks were sliding on ice, they slowed nothing. Operators learned to downshift aggressively, using engine compression to control descent, accepting that once you started down an icy slope, you were committed until gravity released you at the bottom. Getting logs onto the Linn revealed that the machine was only part of a larger mechanical ecosystem. The truck itself had no self-loading capability. It was a tractor and hauler, not a crane. Loading required separate equipment, human coordination, and an understanding of physics that kept dangerous weights from crushing men or smashing equipment. Most operations used a loading boom, a log mounted vertically with a pulley at the top and a gin pole arrangement that let it swing in an arc. Picture a 40-foot fir trunk, 2 feet in diameter at the base, set into the ground with guy wires keeping it vertical. At the top, a sheave wheel, a massive pulley grooved to accept steel cable. The cable ran up and over, down to a load of logs on the ground, and back to a steam donkey engine sitting 100 yards distant. The steam donkey was the muscle, a portable engine with a boiler and a drum that could wind cable with enough force to lift several tons. These machines burned slash wood, the branches and unmarketable pieces left from timber cutting, feeding their own fire from the forest around them. The engineer who operated the donkey watched hand signals from a hooker down at the loading site, translating waves and gestures into precise applications of pulling power. Loading began with the Linn positioned precisely beneath the boom's arc. The operator would back the truck into position, watching the track marks in the ground, adjusting until the rear bunks, vertical stakes that held the load, aligned with where the logs would swing. Get this wrong and you dump several tons of timber onto the ground beside your truck, or worse, onto the truck itself, buckling the frame or shattering track components. The hooker and his crew, usually 2 or 3 choker setters, worked at ground level with the cut logs. A choker was a wire cable with an adjustable loop thrown around a log and cinched tight. The art was in the placement. Put it too close to one end and the log would rotate under tension, potentially breaking free and tumbling. Put it in the wrong spot relative to the log's center of gravity, and it would swing erratically when lifted, becoming a multi-ton pendulum that could crush anyone in its arc. Once the chokers were set, the hooker would signal the donkey engineer. A raised fist meant take up slack. Circular waves meant pull steady. Chopping motions meant stop immediately. The cable would tighten with a musical creaking, steel strands loading under tension, speaking in notes that experienced crews could read like language. Too much creaking meant too much weight or a bad angle, and something was about to break. When the tone was right, the logs would lift from the ground, shedding bark and snow, rising toward the boom's apex. This was the moment of maximum danger. The logs swung free now, hanging from cable that could snap if it had any hidden damage, suspended over men who watched the load like prey animals tracking a predator. The donkey engineer couldn't see the load directly. He was reading signals and listening to the cable. If something went wrong, a choker slipping, a cable failing, men had perhaps 2 seconds to recognize it and dive clear before tons of wood crashed down. When the load cleared the boom top, the swing began. The hooker would signal for slack or tension to control the arc, using cable length to guide the logs toward the waiting truck. This required understanding pendulum dynamics, predicting where the load would swing based on current momentum and cable angle. A skilled crew could drop a load onto the truck bunks within inches of perfect placement. Poor crews destroyed equipment, wasted time fighting loads that wouldn't cooperate, adjusting positions, resetting chokers, arguing about technique while daylight burned and productivity evaporated. The best crews worked in near silence, signals replacing words, experience replacing discussion. They'd learned through crushed fingers, near misses, and occasional catastrophes that efficiency in the woods meant survival. The load chained and the bunks groaning under their burden, the real test began. The Linn sat lower now, tracks settled deeper into whatever surface they rested on. The suspension compressed until you could barely slide a hand between the frame and the bogie wheels. 15 tons total, 7 tons of truck, 8 tons of timber, ready to crawl from cutting site to mill yard through terrain that would defeat anything on wheels. The operator climbed into the exposed cab and began the departure ritual. First, test the brakes. Pull the lever and feel for resistance. Make sure the blocks would actually grip the track drums when gravity demanded stopping. Next, ease the clutch out in first gear without throttle. Feel whether the load would move or whether you needed to rock it free from where it had settled. If the track spun without movement, you'd engage the differential lock, forcing both tracks to pull equally, doubling your purchase at the cost of steering ability. Movement began with sounds that spoke of mechanical strain. The engine note dropped as the clutch grabbed, the governor opened to feed more fuel, and the whole drivetrain took up the slack. Metal groaned as chain drives tightened, and track links found fresh purchase. Then came motion, measured in inches per second initially, the machine overcoming inertia that wanted to keep 8 tons of logs permanently at rest. The first 100 yards told you everything about the haul ahead. If the ground was solid, you'd work through the gears, maybe reaching 3rd or 4th gear at perhaps 5 miles per hour. If it was soft, mud, or deep snow, you might stay in first gear for the entire journey, crawling at walking speed, accepting that the destination was hours distant but inevitable. Steering under load was an exercise in prediction and patience. The conventional steering wheel moved the front wheels, but those wheels were now carrying minimal weight. Most of the truck's mass was concentrated over the rear tracks. To turn, you'd crank the wheel to indicate direction, then use throttle and differential to make it happen. More power to the outside track, back off the inside track, let the front wheels guide while the rear tracks pivoted the bulk of the machine. On hills, physics became a negotiation. Climbing required understanding gear ratios and traction limits. Stay in too high a gear and the engine would lug, losing power, potentially stalling. Drop too low and you'd spin tracks, chewing up the ground without gaining elevation. The sweet spot was found through feel, listening to the engine note, sensing how much the tracks gripped before they slipped, reading the slope ahead to predict where the grade would steepen or where ice might hide under snow. Descending was where operators earned their pay and sometimes lost their lives. The Linn's brakes worked by pressing blocks against the track drums, effective when the tracks had traction, useless when they were sliding. Going down a moderate slope in snow, you downshift until engine compression provided most of your speed control, using brakes only for fine adjustments. The tracks would compress snow beneath them, creating temporary traction, but if you hit ice or hardpack that wouldn't compress, momentum would build like a rolling debt you couldn't repay. The nightmare scenario haunted every operator, starting down a slope only to discover ice at the bottom. You'd feel it in your guts before the machine told you, that subtle acceleration despite being in low gear, despite brakes applied, the terrible realization that you were sliding, not rolling. The only option was to steer for the widest part of the path and pray nothing solid was at the bottom. Trees stopped Linn's, but the operator usually didn't survive the impact. Boulders would tear off tracks. Drop-offs meant the machine tumbled, usually with the load crushing the cab as everything rolled. River crossings existed somewhere between routine and suicide, depending on conditions. In winter, ice could support the Linn if it was thick enough, at least 18 inches for a loaded machine, and even then you'd spread the weight by keeping moving rather than stopping on any one spot. The terror was breaking through, because a Linn that went through ice didn't just sink, it punched down through and hit bottom, trapping the operator in freezing water beneath the cab as the machine tilted forward into the hole it created. Summer crossings required finding fords where the bottom was solid, usually gravel bars or bedrock, and accepting that you'd flood the lower engine components. Operators would disconnect the fan belt to prevent it from throwing water into the electrical system, rev the engine to create back pressure in the exhaust that kept water from flowing into cylinders, and plunge in. The key was maintaining momentum without going so fast that you created a bow wave that swamped the engine. Crawl too slowly and water would find every seal. Move too fast and you'd flood the ignition and stall midstream, with current pushing against tons of log and machine. Solo operation was standard, but profoundly isolating. You'd leave the loading site in early morning, navigate miles of forest road that was really just a slightly less treed corridor between cutting area and civilization, seeing no one for hours. If something broke, and something always broke eventually, you fixed it alone. Thrown track meant hours of work jacking the machine, prying links back onto bogies, resetting tension, hoping you had the replacement pins and tools needed. Engine trouble meant diagnosing by sound and smell, carrying spare parts because the nearest mechanic was a day's walk distant. The best operators developed relationships with their machines that went beyond mechanical understanding into something like partnership. They learned the individual quirks. This Linn pulled slightly left under load. That one ran hot and needed extra cooling brakes. Another had a sensitive clutch that required delicate pressure. They could diagnose problems by listening to the symphony of mechanical noises, distinguishing between the normal clattering and the specific pinging that meant a bearing was failing, or the hollow thunk that indicated a loose track link about to break. The Linn was built for abuse, but physics eventually claimed every machine. Tracks threw themselves most commonly. The endless cycling and flexing would elongate the steel until tension couldn't be maintained and a link would slip off the bogie wheels. This usually happened under load, on slopes, at the moment when you most desperately needed traction. The machine would lurch sideways as one track ran free while the other continued pulling, spinning the vehicle in a circle that could flip it on steep terrain. Thrown tracks in isolation could be fixed with hours of brutal labor. You'd jack the rear of the machine to take weight off the track system, use pry bars to work the loose track back over the bogies, reset the tension with the adjustment mechanism, and pray you'd tightened it enough to hold, but not so much that you'd snap the steel. This was knuckle-splitting work done in whatever weather the forest provided: rain that made steel slick and hands numb, snow that buried tools and made every surface treacherous, summer heat that turned the engine compartment into a radiant oven. Engine failures were catastrophes. These were simple four-cylinder designs, reliable by 1920s standards, but they operated in conditions that destroyed automotive engines within days. Mud would cake the cooling system until the engine overheated. Snow would pack around the exhaust manifold until back pressure stalled the motor. Water from river crossings would contaminate the oil, turning lubricant into grinding paste that ate bearings and cylinder walls. A seized engine in the woods meant abandoning the load and the machine until you could bring draft animals to pull the dead Linn back to civilization. Some operations kept horse teams specifically for rescuing broken machines. The ultimate irony: the animals that were supposed to be obsolete rescuing the technology that replaced them. Getting a multi-ton tracked vehicle out of forest required either another Linn to tow it or a large team dragging it across terrain that fought every foot of progress. Fires were rare but apocalyptic. Gasoline engines leaked fuel from primitive carburetors and cracked fuel lines. Hot exhaust manifolds provided ignition sources. All it took was a leak dripping onto hot metal, and the entire machine could be engulfed within minutes. Operators had no fire suppression beyond dirt and desperation. If fire reached the fuel tank, usually mounted behind the cab, the explosion would throw debris across acres. Several operators died trapped under burning loads they'd tried to disconnect, crushed when shifting timber pinned them while fire consumed everything. Load shifts killed more men than any other single cause. Improperly secured chains would snap under stress, or logs would settle during transport and slip the bindings. A shifting load could roll the entire vehicle, 8 tons of timber sliding sideways, overbalancing the machine, crushing the cab and operator as the Linn toppled. Survivors described hearing the load begin to move, a creaking groan as logs settled, then having perhaps 3 seconds to decide whether to jump from a moving vehicle or ride it out and hope the shift stabilized. Jumping had its own mathematics. Do it wrong, jump downhill while the machine is moving, and the Linn would run you over, tracks crushing whatever they contacted. Jump right, away from the direction of fall if the load was going, and you might land in trees or rocks that would break bones. Some operators rode their machines through rollovers, trusting that the cab frame might create a survival pocket. Sometimes it did. Sometimes they found operators days later, crushed flat beneath machines and loads, death coming from slow compression as their air was squeezed away. Differential failures were insidious because they developed gradually. The mechanism that allowed independent track speeds would wear, develop slop in the gears, eventually fail catastrophically. When it went, one track would lock while the other spun free, spinning the machine in violent circles regardless of steering input. On flat ground, this was manageable. Kill the engine, let momentum bleed off. On slopes or near obstacles, a differential failure meant the machine chose its own direction until physics stopped it against something solid. Cold made everything worse. Steel became brittle below zero. Track links would snap like glass under impact. Engine oil thickened until it barely flowed, starving lubrication to bearings that needed it most during cold starts. Operators would sometimes build fires under the oil pan, heating it enough to pour, risking gasoline ignition for the chance to start the engine. Clutches would freeze overnight, plates stuck together with congealed oil, requiring rocking the machine to break them free before you could engage gear. The maintenance schedule was less a guide than a prayer. Daily greasing of every fitting, dozens of them scattered across the machine, took an hour if you rushed, longer if you did it right. Track tension checks every shift. Oil consumption meant topping up every few hours of operation. Fuel consumption was heavy enough that some operations stationed fuel caches along regular haul routes, barrels of gasoline buried at trail intersections so operators could refuel without returning to base camp. Parts availability was nightmarish in remote locations. A broken track link might require ordering from the factory in Minnesota, waiting weeks for rail delivery to the nearest town, then hauling it by wagon or pack animal to the logging site. Operations stockpiled critical components, extra links, spare chains, belts, gaskets, accepting the capital cost because a machine down for parts was a machine losing money at staggering rates. The financial pressure created dangerous decisions. Operators would nurse failing equipment because downtime was expensive. They'd drive on worn tracks that should have been replaced, would ignore bearing noises that predicted imminent failure, would push through warning signs because the load was worth more than the risk felt dangerous, until the risk materialized and the machine failed in ways that wrecked not just equipment, but the men operating it. The men who operated Linn's formed a distinct subculture within logging camps, recognized by their mechanical skills and the permanence of grease under their fingernails. They were usually younger than the fallers and buckers, men in their 20s or 30s who'd grown up with automobiles and machinery, comfortable with the idea that power came from engines rather than muscle and animals. Repay reflected the skill and danger. A Linn operator might make $4 to $5 a day in the 1920s, when common laborers earned $2. This was enough to save money if you were disciplined, enough to drink it all away on weekends if you weren't. Most operators fell somewhere between, sending money to families while keeping enough for basic pleasures and the knowledge that tomorrow might be their last. Living conditions varied by operation but rarely rose above Spartan. Bunkhouses were uninsulated wooden structures heated by central stoves that kept the area near them roasting while the corners frosted over. Bunks were 2 or 3 tiers high, thin mattresses over wire frames, each man's space about as wide as his shoulders. Privacy didn't exist. The smell was universal: wet wool, wood smoke, male sweat, and the pervasive odor of kerosene lamps that provided light after dark. Food was fuel, prepared in quantities that would stock a restaurant. Breakfast before dawn, flapjacks stacked high, bacon fried in batches, eggs scrambled in pans that needed 2 men to lift, coffee strong enough to strip paint. Lunch was often eaten in the woods, sandwiches thick with meat, cookies that were more lard and sugar than flour, thermoses of coffee that stayed drinkable for hours. Dinner was roasted meat, potatoes, vegetables cooked to submission, pies for dessert. Cooks were respected positions. A good cook kept men working. A bad one emptied camps. The social hierarchy was clear but permeable. Fallers who dropped trees commanded respect for skill and danger. Operators who kept machines running despite conditions held a different respect based on technical knowledge that seemed almost magical to men who'd grown up with axes and saws. Hookers who managed loading crews were valued for judgment under pressure. Everyone looked down on swampers who cleared brush until they needed a path cleared and discovered good swampers were artists who could carve roads from wilderness. Weekends brought the universal pattern of isolated work camps. Some men stayed in camp, sleeping, mending clothes, writing letters. Most headed to the nearest town, sometimes a 15-mile walk, seeking liquor, women, and distance from trees. Drinking was less recreation than release valve, pressure built through 6 days of dangerous work vented in saloons that catered specifically to loggers with money and one night to spend it. Fights were common, but rarely personal. Men would brawl over perceived slights or competing claims to women's attention, wake up the next morning with bruises and vague recollections, and work side by side as if nothing had happened. The violence was theater, performance of masculinity in an environment where actual toughness was demonstrated daily through work that killed the careless or unlucky. Women were largely absent from camps, creating social dynamics that ranged from monastic to predatory. Some men were married, showing photographs of wives and children in distant cities, saving money to return to families they saw months apart. Others formed attachments to women in logging towns, prostitutes, saloon workers, boarding house owners, relationships that were transactional but sometimes genuine in their affection. A few camps allowed married operators to bring wives, creating islands of domestic normalcy in the wilderness. Injuries sorted men into categories. Minor wounds, gashed hands, crushed fingers, burns from hot metal were expected and treated with whatever passed for first aid. Kerosene to disinfect, bandages torn from worn clothing, splints made from kindling. Serious injuries meant evacuation to town hospitals, often carried by the same Linns that moved timber, operators trying to cushion men whose bodies were broken by the same work that employed them. Death was common enough to generate rituals. When a man was killed, his body would be brought to camp, cleaned as well as possible, wrapped in canvas. His belongings, never much, always pathetic in their scarcity, would be gathered for shipment to next of kin. A collection would be taken up, past hat gathering coins and bills from men who knew they might be next. The company would usually pay for transport of the body to wherever family requested, a small dignity that recognized the brutal math. Men were replaceable, but treating bodies with respect helped recruit the next batch. Turnover was constant. Some men would work a season and never return, having seen enough of trees and mud to last a lifetime. Others became lifers, following timber from Michigan to Washington, from British Columbia to California, always moving as the easily accessible forests were cut and operations relocated to the next virgin stand. They'd arrive in new camps with their skills and tools, be recognized as experienced hands, slot into the hierarchy at whatever level their competence demanded. Stories were the currency of evening hours, tales told around stoves that grew more dramatic with each retelling. The Linn that hauled through a blizzard so thick the operator navigated by following his own track scars. The operator who rode a runaway machine down a mountain, steering between trees at speeds that should have killed him, arriving at the bottom with hair turned white. The crew that loaded a record tonnage in a single day, pushing equipment and bodies beyond rated limits. Some of these stories were true. All of them were believed. By the mid-1920s, Linn Manufacturing couldn't build machines fast enough. Orders stacked up from operations across the timber belt, Wisconsin, Minnesota, Michigan, Washington, Oregon, even experimental purchases from Canadian operations working the British Columbia interior. The original design evolved as Holman Linn incorporated feedback from operators who'd pushed his machines into conditions he'd never imagined. The Model C, introduced in 1923, represented the design's maturation. Engine power increased to 50 horsepower with the option of 60 for operations that needed extra pulling capacity. The track system widened slightly, 3.5 feet now, distributing weight even more effectively. The frame reinforcement increased weight but dramatically improved durability, accepting that a machine that weighed more but lasted longer was better economics than a lighter machine that broke frequently. Cab improvements arrived slowly, driven by operator complaints about exposure. Windshields became standard rather than optional. Some models featured actual roofs, metal panels that shed rain and snow but offered no insulation. Windows remained open holes. Glass was added but rarely lasted beyond the first season of branches scraping past the cab in narrow trails. The best operators could hope for was reduced direct precipitation and slightly less wind, not comfort. The transmission system became increasingly sophisticated, offering up to 10 forward gears in some configurations. This gave operators unprecedented control over speed versus torque, letting them fine-tune power delivery to specific conditions. First gear could pull stumps, but moved at a crawl that measured distance in feet per minute. 10th gear on smooth, frozen roads might achieve 20 miles per hour, though this was more theoretical than practical given the routes Linn's typically traveled. Competitors emerged, recognizing the market Linn had identified. Lombard log haulers, Russell snow motors, Holt tractors, each offered variations on the half-track concept. Some used 2 tracks instead of a wheel-track hybrid. Others emphasized different size classes, building machines larger or smaller than Linn's standard models. This competition drove innovation, but also revealed Linn's fundamental advantage. Holman Linn actually visited logging operations, observed conditions, and designed for reality rather than theory. The military took notice during World War I, experimenting with tracked vehicles for European warfare. After the war, some surplus equipment made its way to logging operations, Army machines repurposed for timber. These military conversions proved useful but not optimal, designed for carrying soldiers and equipment, not for the sustained pulling that defined log hauling. They did, however, validate the tracked vehicle concept to skeptics who'd dismissed civilian innovations but trusted military engineering. Railway integration created new operational possibilities and complexities. Some operations built narrow-gauge rail lines from cutting areas to main rail connections, using lins to haul from stump to railhead rather than all the way to mills. This shortened haul distances but required loading-unloading at the railhead, an additional handling step that cost time but enabled access to timber stands too distant for practical road hauling. The Linn cable loader emerged as an evolution designed specifically for log handling. This variant replaced the rear hitch with a powered winch system, effectively integrating the loading boom and steam donkey functions into the truck itself. The machine could drive to a log pile, set its own cables, winch logs onto its own bunks, and haul without requiring separate loading equipment. This self-contained capability made smaller operations viable. You didn't need the capital for multiple machines when one Linn could perform multiple functions. Specialized applications proliferated. Some operators modified Linns for snow plowing, mounting blades and using the traction advantage to clear roads for subsequent equipment. Others used them as mobile power sources, taking the engine's output to run saws or pumps at remote sites. A few operations experimented with passenger transport, carrying crews to distant cutting sites faster than they could walk, though the ride was brutal enough that most men still preferred walking. Geographical adaptations revealed regional differences. Northern operations emphasized cold weather reliability, oil heating systems, insulated fuel lines, enclosed cabs for the genuinely brutal days. Western mountain operations reinforced braking systems and added lower gear ratios for the dramatic elevation changes in Pacific forests. Southern operations, working in swamps rather than snow, modified for extreme mud conditions, even wider tracks, higher ground clearance, sealed electrical systems. The price point put Linn's beyond small operators, but within reach of mid-sized operations. A new Model C in 1925 cost roughly $6,000, equivalent to perhaps 6 months of gross revenue for a productive logging show. Operators who could afford them discovered they paid for themselves within 2 seasons through increased productivity and season extension. Those who couldn't afford them either pooled resources with other small operators or remained dependent on horses and seasonal limitations. Used equipment markets developed as early Linn's wore out or were replaced by newer models. A worn-out Linn still had value to operations that couldn't afford new. The mechanical knowledge needed to keep older machines running was widespread enough that a good mechanic could resurrect machines that manufacturers would have considered scrap. This extended the technology's reach down the economic ladder, putting tracked hauling within reach of increasingly small operations. The 1930s brought changes that would eventually obsolete the Linn's particular solution. Pneumatic tires improved dramatically, larger, tougher, with tread patterns designed for off-road use. Truck suspension systems evolved to handle serious loads without destroying themselves. Road building became more sophisticated, with gravel bases and deliberate drainage that created all-weather surfaces even in formerly impassable areas. But the transition wasn't abrupt. Tracked vehicles remained superior in the worst conditions, even as wheeled trucks claimed increasingly large portions of the work. Operations would often run both, Linn's for the truly difficult hauls, conventional trucks for improved roads and moderate conditions. The economics favored wheels where they could go. Trucks were faster, cheaper to maintain, easier to operate, and didn't require the specialized knowledge that kept Linn's running. World War II created a final surge in demand as military needs consumed civilian production. Some logging operations sold their Linn's to the war effort, where tracked vehicles served in terrain that made forests look welcoming, Pacific Islands, North African deserts, European mud that made northwestern spring look dry. These machines, built to haul timber, instead hauled ammunition and equipment, proving that the fundamental design was sound even when the application changed. The post-war era sealed the Linn's fate. Diesel engines offered reliability and fuel economy that gasoline couldn't match. Hydraulic systems enabled power steering and braking that transformed operator experience. Four-wheel drive trucks could go places that had required tracks, and they could do it faster and cheaper. By the 1950s, new Linn production had ceased, and the remaining machines were aging veterans in a changed industry. Some survived longer than others, finding niches where their particular capabilities still mattered. Remote operations in Alaska used Linn's into the 1960s, working terrain where even modern equipment struggled. A few machines found second lives in snow grooming, their track systems repurposed for packing ski slopes. Most simply wore out and were abandoned in the woods they'd worked, steel slowly returning to rust as forests reclaimed clearings. The environmental movement that emerged in the 1960s and 1970s would look back at early logging with horror at the scale and methods, clear-cutting that left landscapes looking bombed, erosion that filled streams with silt, practices that seemed designed to extract maximum timber with minimal concern for regeneration. The Linn and machines like it were tools of this extraction, enablers of an industrial approach to forests that treated them as resources rather than ecosystems. Yet there's a counter-argument worth considering. The Linn's limitation was also a form of protection. These machines were slow, expensive to operate, limited in capacity. They couldn't clear timber at the pace modern equipment achieved. The forests they worked regenerated, grew back, became forests again in ways that more thorough modern cutting sometimes prevented. The limitations of 1920s technology accidentally created a sustainability that wasn't intentional but was nonetheless real. Collectors and museums preserve a few examples now, restored to operational condition or at least prevented from completely decomposing. These machines sit in carefully controlled buildings, demonstrated occasionally for crowds who marvel at the simplicity and functionality. Guides explain the mechanical principles, show how the tracks worked, sometimes fire up engines that cough to life after decades of silence. But seeing a preserved Linn in a museum is like watching a tiger in a zoo. You understand intellectually what it is, but you miss the essential context of its power. To understand what these machines meant, you needed to see one in mud that swallowed horses, in snow that buried conventional trucks, hauling loads that seemed impossible across terrain that looked impassable. You needed to smell the exhaust mixing with forest air, hear the tracks biting through obstacles, feel the ground shake as 15 tons of machine and timber crawled past. The operators aged and mostly died without fanfare. Old men in retirement homes or family houses, their hands still scarred from track pins and engine maintenance, their backs permanently bent from years in poorly suspended seats. A few told stories to grandchildren who found it hard to believe that machines so primitive accomplished what they did. Most kept their experiences to themselves, having learned that people who hadn't worked in early logging couldn't really understand the combination of danger, difficulty, and satisfaction that defined their working lives. Stand in certain forests today, and you can still find traces. Steel track links half buried in loam that's grown over decades, portions of frame rusting in creek beds where machines broke through winter ice and were abandoned as too difficult to recover. Clearings where bunkhouses stood, identifiable only by rust-stained soil where stoves sat, and the unnaturally flat ground where men leveled sites for buildings. The Linn Tractor represents something larger than one company's product. It embodies an approach to problem-solving that defined early industrial America. Faced with an intractable problem, mud and snow that prevented year-round logging, the solution wasn't to wait for perfect conditions or accept seasonal limitations. It was to build a machine that could work despite conditions, to engineer traction where none naturally existed, to substitute steel determination for impossible terrain. There's a brutality to this approach that modern sensibilities find uncomfortable. These weren't sustainable practices. Forests were cut faster than they could regrow. Operators were injured or killed at rates that would close operations today. Environmental damage was considered acceptable collateral rather than serious concern. The Linn enabled extraction at scales and in conditions that natural limitations would have prevented, accelerating timber harvest in ways that didn't always serve long-term interests. Yet there's also something admirable in the sheer mechanical audacity. Holman Linn saw machines that failed and asked not whether tracked vehicles could work in logging, but what design would make them work. The operators who drove these machines into forests that looked impassable showed a combination of skill and courage that deserves recognition even when we question the larger enterprise they served. The transition from horse to machine, from seasonal to year-round operation, from local to industrial scale, the Linn participated in all these changes, both driving and being driven by forces larger than any single technology. It was part of the mechanical revolution that transformed American labor from primarily human and animal power to primarily mechanical power, with all the benefits and costs that transition entailed. Modern logging bears almost no resemblance to the era when Linns dominated. Computerized harvesters can fell, delimb, and buck a tree in minutes. Forwarders with hydraulic cranes load themselves. GPS guidance and laser range finding replaced the judgment and experience of fallers who learned by watching trees fall for years. The whole process is faster, safer, more efficient, and completely dependent on technologies that didn't exist when Linn's worked the woods. What's lost in this evolution is harder to quantify than what's gained. The intimate knowledge of forests that came from working them at walking speeds, the mechanical understanding that came from fixing machines in the field with basic tools and improvisation, the direct physical connection between labor and result. You cut these trees, you loaded these logs, you drove this machine to this destination, you accomplished this specific, visible thing. The Linn's legacy lives in indirect ways. Every modern tracked vehicle, from bulldozers to military tanks to snow groomers, descends partly from innovations that machines like the Linn represented. The understanding that weight distribution matters as much as power, that traction can be engineered rather than accepted, that hybrid designs combining different technologies might exceed either alone. These principles inform engineering far beyond logging equipment. In the end, the Linn Tractor was a solution to a specific problem at a specific moment in technological evolution. It bridged the gap between animal power and modern machinery, between seasonal limitation and year-round operation, between local extraction and industrial scale. It worked in conditions that defeated everything else, hauled loads that seemed impossible, and enabled an industry to transform itself. The machines are mostly gone now, rusting in museums or forests or scrapped decades ago for metal that served other purposes. The men who operated them are gone too. Their knowledge and experience vanished with them. What remains are the forests that grew back where they logged, better or worse depending on factors beyond the Linn's control, and the persistent human urge to solve problems by building machines that can do what natural capability cannot. So here's to the 15-ton half-tracked beasts that crawled through mud and snow, that hauled impossible loads across impassable terrain, that broke down and were fixed and broke again, but kept working because stopping meant failure and failure wasn't acceptable. Here's to the operators who froze and sweated and occasionally died to keep them running. Here's to Holman Linn, who saw a problem and built a solution that worked despite every reason it shouldn't have. And here's to the recognition that progress is complicated, that the machines that enabled industry also enabled exploitation, that solving one problem often creates others, and that looking back requires acknowledging both the remarkable and the regrettable in equal measure.